towering waves of the sea are one of the Earth's most perilous hazards.
Water is hugely powerful.
Waves have taken lives, they've rewritten maps.
3 killer shock waves rise up from the deep. Rogue.
It flipped over the 60-foot research ship in a matter of a second.
Monster.
It's literally like a catapult. The ocean just turns sideways. It goes boom.
And tsunami.
It can literally bulldoze everything out of existence.
Killer shock waves. Why they're born, where they strike, and how they become deadly forces in the underwater universe. When we see the ocean, we see waves, undulations on the surface of the sea, pure energy in constant motion. Waves can be soothing, or they can be devastating. Energy passing through water, one of the most powerful natural forces on Earth.
Basically, when the ocean decides it's going to rear up its power and try to kill you, you got to predict when that's going to happen and get out of the way.
Towering ocean waves take out swimmers, ships, coastlines, even civilizations.
The sea is so much bigger and so much more powerful than we are, and we don't fully understand it. We don't even sort of understand it.
Waves are an awesome manifestation of the underwater universe. At the extreme are the killer shock waves. They come in 3 types, each bigger and more destructive. Rogue waves, earthquake tsunamis, and monster breakers. But the deadliest wave of all may lie in our future. A liquid behemoth, bigger than the largest wave in recorded history. Will we be ready? The first of the 3 killer shock waves is the Rogue wave. Stealth weapon of the underwater universe.
Where the conditions are just right, a hole opens up in the ocean. And it's a giant pit, and it can come whipping across the ocean at 30, 40, 50 miles an hour. It can move pretty quickly across the ocean and can swallow a whole ship easily.
The definition is usually some huge wave that appears literally out of the blue, that's 2 or 3 times bigger than any of the waves around it.
Even 3,000-ton carriers fall prey to rogue waves.
Between 1990 and 1997, 99 of these bulk carriers were lost, and that's hundreds and even thousands of lives. And we don't hear about it.
They leave behind few witnesses. Yet sailors dating back to ancient Greece tell tall tales of rogue waves.
Waves as high as the stars, where one ship looked like it was on the top of a mountain, the next one felt like it was in a valley.
In the South Atlantic Ocean, one of these rogue waves hits Antarctic explorer Ernest Shackleton's boat in 1916.
He called it a mighty upheaval of the ocean. He said, earnestly, we hoped we would never again meet such a wave, and they were bailing. They were very lucky, actually, to have survived that.
But because reports of rogue waves are anecdotal, scientists dismiss them, like the legends of sea serpents and mermaids. It's not until 1995, at an oil platform in the icy North Sea, that scientists actually catch a rogue wave in the act.
On this particular day, 38-foot waves were rolling through, and all of a sudden, over the horizon comes an 84-foot wave. and it whacks the platform.
Lasers on the platform measure wave heights. This wave is between 2 to 3 times higher than waves on the surrounding seas.
This was the first scientifically confirmed account of a rogue wave. So all of a sudden, the question was not, well, do rogue waves exist? It was, how do they exist?
Normal waves, like these sound waves, show up as regular patterns of peaks and valleys with various frequencies. When the peaks of 2 waves coincide, they momentarily spike higher. But that in itself is not enough to create a rogue wave. A rogue is greater than the sum of its parts. It's almost as if these waves don't follow the usual laws of physics.
A particularly large wave starts to gobble up all the waves around it. So the bigger it gets, the more energy it can take from its surrounding waves. So this is a kind of a vicious circle, a feedback effect.
According to some experts, a rogue wave pirates energy from nearby waves like a snowball rolling down a hill, getting bigger and bigger as it goes.
The bigger it gets, the more energy it can steal from the surrounding waves, so it gets bigger quicker and quicker.
50 miles northwest of Santa Barbara, California, November 4th, 2000. Deadly forces rapidly converge off the coast, silent and unseen. Mark Pickett is a 17-year veteran sea captain. He operates research vessels for NOAA, the National Oceanic and Atmospheric Administration.
That morning when we got up, we were all excited because we could see that the wind was down and we left our anchorage. We could tell that, hey, these conditions look like conditions you never get in this area of California.
Captain Pickett and 2 others board the Ballena, a research vessel with twin 300-horsepower engines.
It was a fiberglass ship about 60 feet long, and it was perfect for what we needed to do with it.
Captain Pickett's mission is to transport Chief Scientist Guy Cochran and technician Mike Boyle to the waters a quarter mile off Point Conception. There, they will work on mapping the ocean floor.
Point Conception is considered to be a very treacherous place. There are several currents that collide there, and in a wave current collision, you get what I referred to as an oceanic train wreck.
Strong waves colliding with a fast-moving current can set the stage for disaster.
This day was so nice, 4 to 6 foot swell with winds that were less than 10 knots. Everything was so perfect that Mike Boyle decided that he was going to take a smoke break.
Out of nowhere, a towering wall of water appears.
I screamed, "Watch out, there's a big one."
It is close to 20 feet high, 5 times taller than all the other waves around it.
As much as I've been out there, I've never seen something like that. I kicked the throttles forward to try to get the ship in the right position to take the wave on the bow.
The Ballena immediately fills with water, trapping all 3 men. Captain Pickett escapes first, followed by Guy Cochran. But technician Mike Boyle is nowhere to be found. Of all the killer shock waves in the underwater universe, the most mysterious is the rogue wave. 50 miles northwest of Santa Barbara, California, a giant rogue wave flips the Ballena, a 56-foot NOAA research vessel, trapping one of the 3-man crew under the sinking ship.
The captain reacted very quickly. That's what you have to do. You may lose, but you still have to try to aim your ship into the wave to survive, and it just wasn't quick enough.
But who can aim at a wave that just suddenly appears? And how does a rogue wave develop out of nowhere on a calm day? A storm half a world away sends wave energy outward in the form of swells. Unlike light or sound waves, as ocean waves become longer and the frequency gets smaller, they also travel faster.
Most people think waves are places where the water is moving from here to there, and it's not really that. It's very odd that the motion in a wave is like, if I hit a particle in a wave, it's doing this. It does this elliptical thing.
Water itself doesn't move much, only a pulse of energy. The rogue wave slips through the ocean the same way energy courses through a cracking whip.
As the wave transports the energy, one of the best analogies, of course, to crack a whip. It's not like the whip goes across the room, the energy goes through in that wave motion.
Long ocean swells can travel thousands of miles without losing much of their energy. If they hit the right combination of shallow depth and strong currents, that energy is unleashed much like a whip, its power concentrated at the tip. The rogue wave that hits the Ballena packs nearly 17 tons per square yard. Trapped inside, Mike Boyle has only seconds left.
As the boat downflooded, it was quite violent. I was tossed and turned. I was rolled upside down. I was banging off equipment and bulkheads, close to just sucking water. I thought, is this it?
Up on the surface, the ship's captain, Mark Pickett, fears the worst.
Guy and I were looking at each other like Mike's dead, and he popped up, and it was just wonderful to see him pop up, and oh my gosh.
Pickett manages to swim 50 yards into shore, only to realize the other two aren't going to make it.
It took me a few seconds to decide whether I wanted to spend the rest of my life dealing with the fact that I lost a ship and I lost the two men who had depended on me as the captain for their lives, or whether I wanted to try to risk my life and go back in the water and see if I could help the guys.
Pickett swims back out. It takes him 30 minutes to pull first Boyle, then Cochran into shore.
He saved my life completely. I mean, there's no way I would have made it. I would have just been fish food on these rocks.
The ship isn't so lucky. The same energy that traveled silently across thousands of miles to swamp the Ballena now smashes what's left of her on the rocks.
It was unsalvageable. We just happened to be at the wrong place at the wrong time, where this bit of energy just happened to manifest itself and take the Ballena.
Rogue waves will continue to draw the attention of scientists until their mysteries have been unraveled.
We really do not know how big rogue waves can actually get. Are they 100 feet? Can they be up as high as 200 feet? We don't know that. We don't have the answers. So part of our work is striving to find answers and understanding the world around us.
So here we have this world full of wonder and this world full of important things that we need to understand, and yet less than a couple % of the oceans have been explored.
We need to sink down 6.5 miles beneath the surface to one of the deepest parts of the ocean. That's where killer shockwave number 2 was conceived, the tsunami.
It's an incredibly dynamic place, the seafloor. About 80% of the earthquakes and volcanoes are beneath the sea.
These regular underwater convulsions are part of the planet's life cycle. Sublayers of the Earth's crust, called tectonic plates, move, grow, and sometimes fracture.
The Earth is not a dead planet. The Earth is alive, so to speak. The plates move. And in the intersection of the plates, where the plates collide with each other, we have earthquakes.
There is one place where tectonic plates may collide faster than anywhere on the planet: the Tonga Trench, located halfway between Hawaii and New Zealand. 35,000 feet below the surface, it is one of Earth's most active earthquake zones.
So on the morning of September 29th, 2009, near the intersection of two plates, there was a really big earthquake, approximately magnitude 8.
The Tonga Trench breaks right where the fault points towards Samoa. When a fault ruptures, it transmits the greatest amount of water wave energy at a 90-degree angle to the fault. like an arrow releasing from a bow.
Once the earthquake happens, all this huge amount of ocean water is set into motion.
That ocean water in motion is called a tsunami. The landmass that lies in its direct path will take the brunt of its force. "100 miles from the epicenter, on the southeastern coast of Samoa, sits the village of Sale Satele. On September 29th, a Peace Corps volunteer from Alabama, Erica Wales, is on the last leg of a 2-year assignment in Samoa.
About 6:45, this big earthquake starts shaking my house, and I had canned food start falling off the shelves. My fan fell off. So I figured I need to get out of the house before it falls down. I actually started texting a friend of mine saying, hey, this is really big.
It lasts several minutes, setting off alarms 2,700 miles away. At the Pacific Tsunami Warning Center in Hawaii, scientists jump into action, trying to outrace the wave. They rely on real-time reporting from a network of ocean buoys.
Out in the ocean, we have these pressure sensors that can detect whether a tsunami wave passed by.
These are called dart buoys. A bottom pressure recording unit sends a signal to the surface buoy, which is transmitted via satellite to the warning center. Using data from dart buoys, seismic sensors, and tide gauges, forecasters calculate where and when the wave will hit, and whether it will flood.
It could be destructive on coastal areas even far from the epicenter.
The warning reaches Samoa 15 minutes after the earthquake. But for most in Samoa, it's too late.
Finally, the earthquake stopped shaking, so I started heading inland.
But this path is the worst place anyone could be.
As I was walking, I could see the ocean, and at that point I saw rocks and coral that I had never seen before at even the lowest of low tides.
Erica is actually seeing the trough of the tsunami, the lowest part of the wave.
We tend to think of waves as the crest coming always before the trough. But the reverse is also possible and happens. It depends on which side of the earthquake zone you are.
At the Tonga Trench, when two tectonic plates collide, something has to give. The denser plate dives down under the less dense plate. On the Samoa side, the seabed drops down, displacing a huge amount of water.
If you're on the side of the earthquake zone that the seafloor moves down, then what you will see first, you are going to see the trough of the wave, like the people were in Samoa. They would see this fast receding tide.
The sea recedes. That means the sea's coming back and you better run for the hills, and it's going to come back not as gently as it went out. It's going to come back fiercely.
At that point, I heard something behind me, and I took a look back. All it was a wall of water. I was worried that this could be the end. It was time to start running.
On September 29, 2009, a magnitude 8 earthquake sets in motion the underwater universe's second killer shockwave, a tsunami. The massive wave, traveling at 500 miles per hour, is heading right for the tiny island of Samoa. In its speed lies its danger. Scientists at Oregon State University's wave tank show how a wave can move so fast. They simulate a tsunami in the lab's large wave flume.
This is a scale model. We should imagine things in real life to be about 500 times bigger. So a house would be the size of a matchbox. Tsunamis affect the entire water column, all the way from the water surface to the seafloor.
To trigger the wave, an engineer sets a giant paddle called a wave board in motion. Energy is transmitted to the entire column of water in the tank.
And there it is, it's coming.
Just like in a real tsunami.
Beautiful.
In the ocean, this water would be 10,000 feet deep.
The tsunami moves at the speed of a jet aircraft.
The water molecules don't move much. Rather, the motion or energy moves through them, like through rings of a slinky.
Its ring of the slinky does not move very far. Yet the motion gets transmitted from one side of the ocean to the other side. And eventually all this energy reaches the coastline and unfortunately tends to have devastating consequences.
After traveling 100 miles in 17 minutes, the tsunami hits shallower water, becoming even more dangerous.
As the wave comes in, it's being forced into a smaller and smaller depth, and that makes it get bigger. The shallow water shortens the wavelength and makes it get higher and higher. You're trying to jam more and more energy into a smaller space.
All that water piles up on itself, forming a single towering wave that advances on the shoreline.
There were places in Samoa that the wall of water might have been as high as 20 feet.
When it smashes into the shore, it's like a freight train slamming into a building. Peace Corps volunteer Erica Wales finds herself 50 feet away from a wall of water as it bears down on her Samoan village.
You can hear the water surging up the river, the trees being ripped from their roots. It was strong. I mean, if it's pulling down all of these trees, like that's a really intense force.
Before it's over, 4 tsunami waves strike Samoa. The water surges inland nearly a mile. 189 people are killed. An hour and a half after the first wave, Erica returns to survey the damage.
When I got there, I was pretty stunned.
The tsunami ripped Erica's house from its foundation.
This is the after picture of the tsunami. You can see there's the roof of the house and all the walls are just knocked every which way.
Yet Erica and the villagers are lucky. No one is killed by the wave.
The tsunami did not destroy my passion for the ocean, even if it is a very powerful and scary place sometimes.
The ocean is our next door neighbor. We need to understand that sometimes this neighbor may be very, very hospitable to us. That sometimes can be, very, very angry.
Earthquake tsunamis will continue to take lives until warning systems can outrace them. But there is another type of wave that dwarfs even the tsunami, the monster breaker, the underwater universe's third killer shockwave. Most waves on the planet are wind waves, and the energy that generates them begins 93 million miles from Earth.
Energy to produce waves comes from the sun. Solar energy heats up the surface of the Earth, the surface of the planet, but it doesn't heat it up evenly. It heats up the equator differently from the way it heats up the poles.
The uneven heating of the globe creates wind. Wind blowing over a flat ocean surface pushes the water in little turbulent bursts, creating small ripples called catpaws.
Catpaws is the mariner's name. Capillary waves is the scientific name. And they're the key, actually, to bigger waves being generated because the wind has to have something to press against to make them bigger.
The oscillating pressure and the frictional drag of the wind on the ocean transfers energy from the air to the sea, where it's expressed as wind waves.
It goes back to those very basic laws of physics that you have a body in motion, water, putting a force on it, that's the wind blowing, and that water will essentially start having motion to it.
But the monster breaker that competitive surfers want demands something more. Giant storms. Like egg beaters, these weather systems put energy into the water in the form of very long waves called swells. Swells can travel thousands of miles across the ocean, leaving the storms and the wind that produce them far behind.
Wind is what fuels the giant ocean waves, the ones that these big wave surfers are looking for. And the longer the wind pumps energy into the ocean, the bigger and more fully developed the waves will be.
Monster breakers require three things: extreme winds, blowing a long time, over thousands of miles. The long ocean swells reach shallow water, which steepens them to dramatic heights, until they break.
Surfing is a way where you can really get close to the energy of the ocean.
25 miles south of San Francisco is a place called Mavericks, one of the most dangerous surf spots in the world.
Mavericks water is quite cold. It's all black. The idea of being at Mavericks is just a little spooky.
It's not just a wave, it scallops up like a big old clamshell and just heaves over and does that giant curl, that giant lip, and just hits all the way out to the flats of the trough, and it explodes. Amazing power.
The waves at Mavericks are huge. On the biggest days, they approach 60 to 80 feet on the face. A lot of guys that first came and surfed Mavericks, right, when the first thought was someone's gonna die here. You know, people are gonna die here. That's the kind of wave it is.
Why do the waves at this spot jump up, when just around the corner, the harbor lies still?
When waves come into shallow water and the middle part of the wave slows down, it's going to bend.
This is called refraction. When a point of land sticks out into the ocean, the shallow water near it slows and focuses the waves, much like a magnifying glass focuses sunlight.
Waves come in and then they focus in onto one spot, so the energy is concentrated.
The Mavericks monster only shows up when conditions are perfect. For years, only a few locals dare to surf there, including Grant Washburn. But in 1994, Mark Fu and Ken Bradshaw, two of the best big wave surfers on the planet, decide to challenge the monster wave. These men will learn a tragic lesson, that the winner is always the underwater universe. The third killer shockwave in the underwater universe. An elusive monster breaker the size of a 6-story building. It rears up infrequently at a surf spot 25 miles south of San Francisco called Mavericks. In 1994, Mavericks is just beginning to attract the attention of the superstars of the surfing world.
Wow.
Veteran surfer Ken Bradshaw is one of them.
Mavericks became the new K2. It might have been Everest, but we weren't sure. But it was definitely a K2. It was right up there. There was some unreal waves out there.
Bradshaw's younger rival, Mark Fu, also wants a chance at K2.
Mark Fu was this high-profile younger surfer, was trying to make a name for himself. So he was always this kind of brash, pushy, aggressive surfer.
My life is surfing, so...
36-year-old Fu is known for his fearlessness and his single-minded pursuit of publicity. Bradshaw has had his issues with Fu's quest for fame, but by 1994, he considers him a friend and a friendly rival.
They were rivals, and they definitely pushed each other's buttons, but they also were two of the only guys that were really doing that in the water.
But in order to challenge each other atop Mavericks' monster breakers, they need a perfect storm to hurl the waves into action.
You'd have to look into the past to find out where they came from. When you're looking at waves, you're kind of looking at a story, that's something that happened days ago and on the other side of the world.
In this case, a storm on the other side of the Pacific sets off the long-awaited chain reaction.
Storms that are born in Japan and then head to Alaska and sort of brew and get stronger in the Gulf of Alaska come down, and if they hit at a certain swell angle, it hits this ledge and forms the wave.
The waves that hit the ledge at Mavericks are some of the biggest local surfer Grant Washburn has ever seen.
Oh, it's still happening. The 2 or 3 days early in this week of December of 1994, there was a series of storms that happened all in a row. And we had like the best waves for 10 days that we'd had in years.
Word reaches Fu and Bradshaw in Hawaii.
Somehow Mark had found a way to get a couple of tickets. So he said, yeah, look, I got tickets. You want to go? Okay, I'll go.
On December 23rd, 1994, they arrive at Mavericks to see for themselves what kind of waves the storms in Alaska have delivered. They are big, very big. Waves are measured 3 ways. Wave height, from crest to trough. Wave period, the time between 2 crests passing the same point in space. And wave length, the horizontal distance between 2 crests.
If we think of a wave as a sine curve, the distance between the waves from peak to peak is actually more relevant to the surfer than the height of the wave, because there's so much energy stored laterally on the surface of the ocean.
The wave length of the swell that will hit Mavericks is very long, meaning each wave contains an enormous amount of energy. After traveling 2,000 miles from Alaska for 2 days at 60 miles per hour, the monster breakers are finally in town.
It's a beautiful sunny day. Took the long walk out, talking about the break all the way. The water was not terribly cold. We get in the lineup.
The waves that day obey the laws of physics, except that they're on steroids.
The tallest part of the wave and the first part to break is the apex. That's the center part. That's where we want to catch it.
With water at the apex falling as fast as 33 feet per second, it's also the hardest place on a monster breaker to take off from.
It's the most desirable part of the wave to be on a surfboard because it's got the most energy. So it's pushing you along faster and it's more critical.
Taking off from the apex delivers the greatest velocity, like skiing down the steepest slope of a mountain.
The first piece to fall over, that's called the lip. If you're under it, you can ride the wave. If you do it right, it's a huge thrill.
But on this day at Mavericks, the thrill of coming out on top will exact a high price.
We're surfing for a while. After a few rides, I asked Mark, you having fun? He goes, oh yeah, I'm having a great time.
The unwritten rule in surf culture, the man closest to the apex has priority for that wave. At 11:20 a.m., both Fu and Bradshaw paddle for the same monster.
To hell with etiquette, you could see it in his brain. I want this wave, it's a good wave. He wanted it. So I just put my legs in the water and I pull back. Figured let Mark have it, he's going.
In this video, Mark Fu takes off smoothly. Then something goes very wrong.
He fell on his stomach. He got sucked over in a part of the wave.
As the wave shifts, Fu falls violently off his board. Then the entire weight of the wave crashes on top of him.
Water's quite heavy. A cubic meter of water weighs a ton.
Trapped under a wave, the surfer can spin end over end, caught in a vortex of energy powerful enough to snap steel.
Feel like the wave's trying to rip your arms and legs off. It's trying to pull you in all directions at the same time.
Surfers have been known to survive the impact of up to 3 successive waves before resurfacing. But in this case, wave after wave passes by with no sign of Fu.
I get to the beach and somebody comes running up to me and he's got this really weird look in his face. I'm going, uh-oh, something's wrong. So I went on board and, of course, identified him. In absolute disbelief, I just picked him up and held him in my arms and said, "Why, Mark, why?" He was the first big wave rider to actually die surfing big waves. He was the first.
Mark Fu is killed by not just one, but a succession of monster breakers.
At Mavericks, the wave controls the energy of the surfers. That's not true on most spots. Most surf spots, the best surfer, can pretty much dominate the waves. At Mavericks, the waves dominate everybody, including the best guys in the world.
Before the Mark Fu incident, they didn't really think that you could die in big waves. And that was a kind of reality check for the guys who surfed Mavericks at that time.
As terrifying as these waves are, there is another, even more devastating killer shockwave. Its origin lies outside the underwater universe.
There's a type of tsunami that we typically call impact tsunami, and that's when something from above the water crashes down into the water.
The impact tsunami. When mass from above impacts water below, the ocean responds with a killer shockwave unlike any other. Just such a wave is created in August of 1883 when a massive volcanic island in Indonesia, Krakatoa, erupts.
Suddenly, without any real warning, there was a titanic explosion where the entire island essentially vaporized in a microsecond.
2/3 of the volcanic island falls into the ocean, setting in motion 4.8 cubic miles of seawater.
There was what we call a flank collapse. A piece of the volcano actually collapses into the water, displaces water sideways.
Unlike an earthquake tsunami, in an impact tsunami, the closer you are to the source, the bigger the waves.
We're talking about a wave which, from anecdotal evidence, seems to have been about 130 feet high.
The Krakatoa wave is the largest impact tsunami in recent memory. But it pales in comparison to the biggest recorded wave in Earth's history. An event so destructive, it wipes out more than half of all living species. And it's just a matter of time before it could happen again. The deadliest, most powerful killer shockwave in the underwater universe is actually conceived in outer space.
65 million years ago, there was an asteroid in space. We think we might even know where the asteroid came from, what its parent family was.
This asteroid has a date with Earth.
The asteroid was 10 miles across. You know, this was no small rock. This was a mini planet.
Traveling 45,000 miles an hour, 20 times faster than a rifle bullet. The impact with Earth unleashes the equivalent of 100 million tons of TNT. It destroys up to 70% of Earth's species.
The asteroid that 60 million years ago apparently wiped out the dinosaurs and much of life as was known at that time, created this huge crater north of the Yucatan Peninsula.
A crater believed to be 120 miles wide and 1 mile deep.
The ocean was about 50, 100, maybe 200 meters deep at this point. You can think of it as a basketball splashing in a puddle and splashing water all over the place, but the real event is the massive hole you made in the ground. And now all the oceans want to rush in to fill this hole.
As water rushes in, a wave train moves back out, causing a tsunami as high as the Empire State Building. An expanding ring of waves radiates outward in all directions.
It takes about 24 hours for a tsunami to wrap around the Earth. And the next hour determines the fate of the rest of the planet.
The wave generated by the asteroid strike inundated Europe and inundated the southern coasts of the continent that we now call North America. It swept around every ocean on Earth, absolutely disrupting and destroying most of the life in the sea.
Even today, there are still traces of the ancient cataclysm.
The best record you find of it is these little tiny pieces of meteorite down on the seafloor.
To retrieve this evidence, scientists need to dive down into the carbon and sulfur-rich rocks beneath the Yucatan.
You can drill and find sediments that were laid down around that time. Pick up bits of the asteroid that struck the Earth. And so that's the smoking gun.
Asteroid impacts are not a unique event in Earth's history.
We get hit by something the size of a Volkswagen about every 2 weeks. It ends up exploding in the atmosphere.
Could an asteroid the size of the one that hit 65 million years ago strike again?
There's absolutely no question that another asteroid is going to hit the Earth.
With 70% of the Earth's surface covered by water, it's a better than 50-50 chance it's going to hit the ocean.
If it hits water, the resulting waves could be monstrous.
They can be as high as the ocean is deep. And if you have a big enough asteroid, you can make an ocean wave 5 miles high. I don't think people really appreciate this. It's actually the tsunami that's probably the biggest risk that we have to fear from asteroid impacts.
Outside the sun, killer shock waves are among the most powerful elements that we contend with on planet Earth. Rogue, monster, tsunami.
The ocean has endless amount of energy. You can only get close to understanding it and matching it, but you can never conquer. And I think that's the respect we all have for the ocean. We just try to work within it.
Some experts fear that waves could grow more dangerous in the coming years. They are concerned that climate change could potentially generate more and more powerful storms that would in turn create steeper seas.
No matter where we live on planet Earth, we have an impact on the ocean, one way or another. Conversely, no matter where you live on Earth, the ocean has an impact on you.
There's the water again, it's hitting again.
Look at our track record as a civilization. It's in our best interest to understand the ocean and learn how to use it wisely.
While we may think we can direct our destinies, killer shockwaves remind us we do not.
Once you're at sea, you're all alone, and there's gigantic waves in a storm, and you realize pretty quickly how insignificant you are.
If you stand in front of a 70-foot wave, you can't think, hey, I'm running the show, because that illusion is just shattered. And I think awe is the proper emotion to talk about. It's a mix of beauty and terror. People have nightmares about it. It seems to be almost a universal vision. You can't stop it. You can't do anything about it. You are completely powerless.